Good morning. We're going to do more asymptotic notation today. We're going to sort of complete the quintet of definitions that you'll need to know. And amazingly enough, that'll be it. There's going to be a bit more to talk about with asymptotic notation, but it'll not involve these inequality or quantifier-based proofs. And then after that, the math portion of the course is done. It feels like just yesterday I was talking about how the first 2 weeks of the course are going to be like crazy, weird math stuff, and then we're going to chill out and do some programming. That day is almost upon us. So we have functions f of n equals n squared log base 3n. And we have g of n squared. And we've got 5 sort of true or false statements, all based on asymptotic notation. The first 2 you saw last class. And I'm going to write out what each of these symbols are sort of like in terms of numbers. So if f is in big O of g, it's as if f is less than or equal to g. Big omega is like greater than or equal to. And these are in terms of asymptotic growth. Like, another term for this is limiting behavior. Basically, how it acts as its input n goes to infinity. And of course, the functions f and g are not necessarily equal. They're not necessarily always less than or greater than. That inequality isn't always true, but it is true as n goes to infinity. So anyway, today we're going to learn about 3 new bits of asymptotic notation. This one, big theta, is like f being equal to g. So they will grow at roughly the same rate. Little o is like being strictly less than. As n goes to infinity, the value of f of n will be way smaller than g of n. And finally, little omega is like f being strictly greater than. I'm gonna try to check out Desmos. Hold on. Yeah. Oh. And I'll type in the 2 functions that we were working with. Is this not going to let me change the base of the log? If it doesn't, that's not the end of the world, because it turns out all log functions are asymptotically equivalent. They're all in big theta of each other. So the results of what I'm about to show you don't actually depend on whether I use log 3, log 10, log 56,000. but I'm going to try a bit harder to get a subscript. Uh-huh. Okay, we have our red function of x squared times log base 3 of x, and a blue function x squared. And also, for the sake of using the definitions of those bits of asymptotic notation, I'll add the constant multiple m. So we see that as x gets larger and larger, f of n, so x squared times log base 3 of x, eventually becomes greater than g of n, x squared, and stays that way. Notably, this is true no matter what I set m to. Yeah. So if I set m to like 100, I could scroll up and to the right for like a couple hours, but I would eventually find that f of n overtakes g of n. No matter what m I choose, this will lead into the definitions of little o and little omega. Oh yeah, actually, we're going to keep graphing. So now we have the function x squared plus 2 to the x. Keep in mind that we're using n on the slides and x in the graphing calculator, just because if you try typing n into the graphing calculator, it'll think that it's a constant and get confused. Nah, that's not very helpful. These functions are so close to each other that it's kind of hard to illustrate the inequalities that I want to show, but we're going to bear with it. So we have a function that contains an exponential term, and we're comparing it to different functions. So is n squared plus 2 to the n strictly less than n squared? No. We see that the red function goes above, or the red line goes above the blue line pretty quickly. And if we use the definition of little o, which we'll see soon, then you would be able to prove that this relation is true. So what about x to the 4? Ooh, x to the 4 grows pretty fast. But we have control over the constant multiple m as well. We just need to find some constant multiple such that the inequality is true, and lo and behold, f of n eclipses it eventually. What about 2 to the x? Oh. these two functions are, as it turns out, asymptotically equivalent. So it's like they're equal to each other. They're in big theta of each other. And that means depending on how you set m, you could have the red line overtaking the blue line or the opposite. Both of these can happen. And finally, I think I'm gonna rush through these last two because I wanna get into like the real stuff with the definitions. But 3 to the n is asymptotically greater than 2 to the n. No matter how we set m, the blue line will eventually be above the red one. And finally, x factorial. Yeah. Gets greater than our f of n very quickly and stays that way. And an interesting property that will probably be relevant later is that this all sort of depended on the largest term in f of n. This n squared actually didn't end up affecting the results at all. We would have gotten the same results if we had f of n equals 2 to the n, and we would have gotten the same results if we had f of n equals 2 to the n plus n squared plus n cubed plus 1/2 n, whatever. Exponential functions like 2 to the n are larger than any polynomial. We'll formalize this later. All right, finally, definition. I was getting tired of hand waving. This is the longest definition we'll cover in this course, but it's actually quite sensible if you know big O and big omega, and we'll just break it down. So we have 2 of these m variables existentially quantified, and then n naught existential and n greater than n naught universal, just like you have already seen before. And then instead of one equality, you have 2. You need f of n to be greater than one multiple of g of n and less than another multiple of g of n. If those are both true, then f of n will be in big omega of g of n. So as a simple example, consider the function 3x, 3n or whatever. I'll just use a different letter for this, even though the slides use subscripts M1 and M2. Capital N. Okay, so say we were trying to show that the function 3x is in big theta of x. So 3x and x grow at roughly the same rate asymptotically. And as always, using the graphing calculator could be a good way of finding m values. Certainly a good way to visualize these concepts, but are not always reliable because they might give you some values that are hard to work with. I remember getting a value with a really long decimal part last class. So I recommend using the graphing calculator for more of a conceptual overview of this. But then when you're doing serious work, do it algebraically. Anywho, I'm going to set m to 5 and just keep n at 1. And we see that our function is in between those two multiples of x forever. So 3x is in big omega of x. Now let's try something that is not in big omega of x. Let's say x squared. So it's really easy to find a multiple of x such that 3x squared is greater than x. We're just going to keep n at 1 still. But we're going to have a really hard time finding an m such that 3x squared is less than x. Both of those inequalities need to be true for it to be in big omega. I'm going to crank them up. Yeah, seems like with m equals 100, we're going to have the inequality 3x squared less than mx forever. Actually, this is too much scroll. Again, the point is going to hold no matter what m I choose. This is just for the sake of me not having to spend forever scrolling up. Aha! 3x squared eventually overtakes it. Turns out it's impossible to bound 3x squared between two multiples of x like that. So we say that 3x squared is not in big omega of x. 3x squared asymptotically grows faster than x. So to show algebraically that a function is in big omega of another function, sorry, not omega, theta. Have I been saying omega this whole time? If I have, I meant theta. So it's going to be a very similar process to past definitions and their proofs. We're just going to have to show that two inequalities are true. So this is saying for all, or there exists an m1 greater than 0 and an m2 greater than 0. Such that there exists an n not greater than 0, such that for all n greater than n naught, 5n plus 1 is less than or equal to m1 n, and 5n plus 1 is greater than or equal to m2 n. I'm just going to make sure I have those subscripts, right? So m1 should be the small one. I got it in reverse. Okay, so like I said, similar process. We're just going to have to solve two inequalities separately instead of one. And thankfully, they don't really interact with each other. It really is just doing the familiar task twice. So, rough work for the first one. For this one, we could use the really simple trick, drop unneeded terms. we see that 5n plus 1 is greater than or equal to just regular old 5n. Cool. So now we have a simplified inequality. We're going to reverse engineer that now. For a very simple m has to be less than or equal to 5. So real proof, we're going to write, m1. m1 has to be m1 has to be less than or equal to 5. So we're going to write m1 being equal to 5. You could have wrote m1 equals 4, 3, 2, whatever. It's just nice to choose the value that is like closest to the inequality you find. I wanted to do this one entirely on the slide. I think I'll have to delete this. Yeah. Sorry. So now for the other inequality, we're going to do something slightly more complicated, but still manageable, I hope. We won't be able to drop unneeded terms because we're trying to find something greater than 5n plus 1. But we can just use the good old rounding up trick. If we guess that n is greater than 1, then we can just turn that 1 into an n, because 5n, or from n greater than 1, it'll follow that 5n plus n is greater than 5n plus 1. We assume that the simplified inequality is true, reverse engineer it to find a value. And we get a bound on m2. Keep forgetting these subscripts. So m2 has to be at least 6, and we're going to choose 6. The rest furthers the thing I've been saying about how big omega proofs are really just doing both a big O and a big omega proof. Big theta proofs are like that. So you prove that both inequalities are true. The first one is really simple. The reverse of that drop unneeded terms trick is to just bring in another term. And then the second inequality uses the rounding up trick in reverse. It shows that the inequality is true. Good stuff. So what about a function not being in big theta of another function? You'll have to negate the definition as usual, and it'll result in a slightly different proof structure. So, excuse me. It starts off familiarly enough. We just took all of the existential quantifiers, turned them into universal quantifiers, and universal turned to existential. So far, it's the exact same as big O or big omega, except there's just another constant multiple hanging around. But then it gets kind of weird, kind of cool, maybe. Before, we had two inequalities that needed to be true. It was an AND statement. We negate that, and that's an OR statement of the AND statement's components negations. So we have that for all these quantified variables. M1 times G of n has to be greater than f of n. or f of n has to be greater than m2 times g of n. It's an or, so you only have to prove one of these in order to prove the overall statement. In fact, it's very likely that only one of these is true, but that's fine. Only one of them has to be true for the or statement to be true. So you'll have to do a bit of rough work in your head, apply some intuition to figure out which inequality to go for. You might want to use the graphing calculator for this, but in this case, there's something even simpler that we could do. Looking at the largest terms of each function, we see that the largest exponent in f of n is greater than the largest exponent of g of n. So f of n is probably going to be the one that grows asymptotically faster. So this one is probably going to be true. And we can just ignore this one. And I strongly suspect that the inequality with M1 is just straight up false. So we have the inequality that we want to prove being n cubed being strictly greater than m2 7n squared plus 1. And from there, it becomes more familiar. We're going to try to simplify this complicated side. As a general rule of thumb, if you see addition in the complicated side, you're probably going to use the rounding up trick. If you see subtraction, you're probably going to use the factoring trick. So in this case, we could guess n greater than 1 and end up with an expression in which we replace the 1 with another n squared term. I'm just going to write that from n greater than 1, it follows that n squared is greater than 1. So then we simplify to 8m2 n squared. We assume that the simplified inequality is true, just like we assumed the original inequality was true, for the sake of finding a value that fits it. And this one's going to be easy now. I'm going to just divide both sides by n squared to get n being greater than 8m2. So for setting n, we got that it has to be greater than 8m2. And then we have another constraint that we sort of glossed over. It was shown implicitly. N has to be greater than n naught. And n naught is arbitrary, so we just include n naught in our max function. Additionally, we found that n has to be greater than, yeah?
It's supposed to be n,
Uh,
divide n cubed by n squared. Last.
Like here?
Yeah.
Yes, thanks for pointing that out. Oh yeah, we found that n has to be greater than 1, but that one's sort of just covered by the trick that we learned earlier to make sure that n is strictly greater than both of these. Oops. Adding 1. So, since we add 1 to these, it's like these two things, it's already guaranteed to be strictly greater than those. And since they're both guaranteed to be strictly greater than 0, as shown here, the result will be greater than 1 as well. After last class, a student asked me about another trick to set n, asked me if it was valid, and it was. You might want to use this. You could also say that n is equal to the sum of all your constraints. This works. Since all of those terms are guaranteed to be positive by definition, their sum will be greater than any of their parts. If you do this, just be cautious and make sure that all of those terms are positive. If any of them are 0 or negative, then this could result in an n that doesn't follow one of the constraints. So we set n according to the quantifiers, and then we just show that the desired inequality is true. We eventually prove that the inequality involving M2 is true, and that proves the whole thing. It's an OR. We don't care about this. Any algebra worth pointing out? Not really. I'll just say again that a helpful study technique will be to look through these proofs and make sure that you understand all of the steps. Like this step and that step rely on the definition of n in ways that may be unintuitive. Okay, so we're going to do another proof of something not being in big omega. I think this time we're going to use the inequality with M1, but we'll see. Looking at the two functions, the trick about the highest exponent, or the term with the highest exponent, letting you judge which one is probably greater than the other, basically also applies to exponentials. We can check out the largest base of all the exponential terms, and the one with the largest base will be the fastest growing one. In this case, we have 6 to the power of n here and 3 to the power of n here. Since 6 is greater than 3, this one's going to grow way faster. So we're most likely going to use this inequality. This example, I think, is kind of neat because you might have noticed a giant minus 5 f of n here. Minus 5n here. And you might think that that counteracts the 6 to the n. Maybe like it would turn it into 1 to the n or something weird like that. But no. Exponential functions grow crazy quickly. And it turns out that 6 to the n is just so much larger than 5 to the n that subtracting 5 to the n from 6 to the n doesn't change a thing. The function still grows faster than 3 to the n. So we're going to try to prove this inequality true. And like always, we have a complicated side that we want to simplify. We're going to use the factoring out trick here. The tell was that there's a subtraction. Exponential functions are very different from polynomials, but thankfully the same rules apply in this specific context. I'm going to factor out sort of n from this fraction. And then we'll see the factoring out trick working like similarly but differently to the equivalent one for polynomials. Before I had a fraction of a fraction with a large power of n in the denominator. Now we have a fraction raised to the power of n, but the same idea still works. It sure would be nice if 1 minus 5 over 6 to the n just turned into 1 minus 5 over 6. So I'm going to say that n should probably be greater than 1, so that this whole thing can be greater than a similar expression, but with that fraction raised to an exponent replaced with just a fraction. You might be tempted to simplify these two things, turn that into 6 to the power of n minus 1, but it turns out to be counterproductive. Our goal is to easily compare this with 3 to the n, so we're going to split up 6 to the n as shown. Also, I'm going to draw 1 over 6 m1 like that. Cool, you can do that. This is a good enough simplified side. So we're going to now use this, turn that into the simplified inequality. And now that there's only one term in each side of the inequality, we're prepared to solve for n. I'm going to divide both sides by 3 to the n. Isolate n. And finally, make it in terms of n. This last one is not as clear as most of the operations I've been doing on inequalities. But remember, the inverse of an exponential is a logarithm. So we're going to take the log base 2 of each side. So now we have two constraints on n that will allow us to start up the main proof. And the main proofs algebra is like the rough work in reverse, as usual. I think if I have time at the end of a class, or the end of this class, I'll go through one of these examples in more detail, because like, this is the part that gets you marks, and I'm totally glossing over it. It is important to show you how to start the part that's worth marks. But you might deserve a bit more explanation on the part that actually gets you marks. But what you deserve more is more definitions. Yeah, good enough segue. We're going to learn about little o and little omega now. Remember that their big counterparts were like less than or equal to and greater than or equal to. These ones are like less than or strictly less than and strictly greater than. It will take a while for this ordering of functions to sink in. The first slide of this lecture is helpful to refer to for the sake of building intuition of which functions are greater than each other. And I don't remember where I was going with that. Oh yeah, I was going to say that it probably isn't immediately obvious what the difference between less than or equal to and strictly less than is. So I think we'll check out some more graphs. Yeah, sure. Both of these functions, 4.7x and 0.6x, they're considered equal asymptotically. Just because there are other functions that grow way faster and way slower. So 4.7x would be in big O of 0.6x, but it wouldn't be in wouldn't be in little o. Little o would be reserved for functions that grow way faster. Like both of these multiples of x would be in little o of x squared. This reflects how they're at a lower stage in the hierarchy than n squared. I think this will all come together next class when we look at more properties of asymptotic notation. You'll see what the sort of families of functions are. Oh yeah, and I guess speaking of families of functions, it's worth pointing out, although this has already been shown implicitly, that all these things, like little o, little omega, big theta, whatever, they're all sets. The set little o of g of n is the set of all functions that grow way slower than g of n. Big theta of x, which contains all of the functions that grow at roughly the same rate as x, would contain both of those functions no matter what you set m and n to, but it would not contain x squared. Anyway, let's talk about the definitions. These are very similar to their big counterparts to the point that it, may be likely that you'll confuse them. The only difference, it turns out, is this one quantifier. Even this inequality doesn't change. Even though it's kind of frustrating that it doesn't, you'd think that it would change to reflect this. Nope, it doesn't. Oops. This basically works to prevent some edge cases where the two functions are exactly equal for a specific m. You're just going to have to deal with it. In the course Comp 2080 Analysis of Algorithms, you might be able or might be asked to memorize this, in which case I would very much stress that it's the exact same except the quantifier. But in this class, you'll only have to ever recognize the definitions, not the same as recalling. So I'll still stress it, but not as much. The definitions are the same as their big counterparts except for one quantifier. And this sort of encapsulates the notion of a function being greater than another. Like I mentioned before, mx and nx are in big theta of each other. They're also in big O and big omega of each other, because they're less than or equal to and greater than or equal to each other. We can see that mx is in big O of nx, setting n large enough that mx is less than or equal to nx. But no matter what you set m or n to, neither of these functions will have the inequality whatever x is greater than, no matter what constant multiple you choose, the inequality x squared is greater than or equal to mx will always be true. Okay, let's do our first proof with one of these. As always, the first step is to remember the definition and figure out which inequality you're going to prove. So remember, it's for all m greater than 0, and the rest is the exact same as the definition you already know. Now, which symbol are we using again? Okay, big omega. So n to the power of 7 plus 8 and 6 will be shown to be greater than n to the 5 plus 1. Very sad, we have two sides of the inequality that both have two terms, so we're going to have to simplify both of them. Gross. Luckily, we see that this one's a sum where the simplified version of it is going to be greater than? Ah, crap. I thought we were going to be able to use that drop unneeded terms trick, but nope. We're going to have to do something more complicated. I was hoping that this simplified side would just be n to the 5, but that's clearly not greater than or equal to n to the 5 plus 1. Oh well, maybe we'll be able to use the trick here. Thankfully, it's not that much more complicated. We're going to use the rounding up trick. say that n is probably greater than 1, which implies that n to the 5 will be greater than 1. And we end up with a simplified right side of 2n to the power of 5. Now let's do the left. Okay, let's see. We gotta find a simplified side that is less than the original side. Can we use the drop unneeded terms trick? Yeah. N to the power of 7 is less than n to the power of 7 plus 8n to the power of 6. I guess this depends on the assumption that n is greater than 1? Oh no, actually, shout out to another student who talked to me after class. You might remember in a previous lecture we had a similar case where we had like some function of n plus n squared, and I used the drop unneeded terms trick on the basis that n squared is going to be positive if n is positive. Well, that's an even power of n, and those are always positive, regardless of the sign of n. So in that n squared case from last lecture and the n to the power of 6 case right now, the use of this trick doesn't require any assumptions about n. It's just always true. And I think that's neat. Okay. So we're going to make the simplified inequality now. Okay, so I kind of botched this one, even though everything I did was correct. It's going to lead to a slightly less elegant choice of values, and you're going to see why soon, and then I'll correct my mistake. Let's solve for another constraint on n, which will indirectly solve for n squared. Divide both sides by n to the 5. N squared is greater than or equal to 2. Okay, square root. Yeah, good enough. However, we could have done a different simplification earlier that would have let us make a constraint of n that is an integer, which is slightly nicer. See here how we just said that n to the power of 7 is less than itself plus 8n to the 6? Well, what if we just did the opposite thing, drop n to the 7? This is also true. Briefly forgot how to draw an 8. So then, after dividing both sides by the smaller power of n, we end up with an inequality that just has n on one side. And then this is slightly better. We can do even better though. this side, we can sort of continue to drop unneeded terms. We know that 6, or n to the 6 is always positive, so multiplying it by 8 is going to make it bigger. Not multiplying by 8 is going to make it smaller. Ta-da! All of the values of n that I found are valid. All of them would work to actually do the proof. But integers are just generally nicer to work with. So it may be worth spending time trying to simplify your inequalities just right in order to get constraints that use integers. Oh yeah, also dropping n to the 7. Sadly, 7 isn't an even number, so you actually do need to make the assumption that n is greater than 1 here. Oh well. I'm going to keep dwelling on this for a little while because while I was partway through that other explanation, I thought of an even neater trick. It's like an expanding brain meme. The first one was like the small brain. Now we got the big brain here. And we're about to go galaxy brain. So going back to our constraint that n has to be greater than the square root of 2. Well, you know what's a choice of n that is greater than the square root of 2? 2. Without any sort of extra algebra, we're just allowed to choose that because these are constraints, not actual specific values. Oh man, 2m? Did I do something wrong? Oh, shucks. I totally forgot to put m around here. Thankfully, this will only require minor revisions. Everything on the right side still works if you multiply it all by m. Actually, I think I'll write it as 2m instead of m2 to avoid confusion with m subscript 2. Cool. This goes back to the idea of satisfying multiple constraints from previous classes. When you have multiple constraints that are all just specific numbers, and it's all n has to be greater than that specific number, you can just choose the maximum of those. When your constraints involve variables, use the max function to sort of automatically, even programmatically, choose the greatest of those values depending on what m is. And then we do the good part. This step uses the rounding up trick in reverse. And this step uses the fact that m is greater than 2m. And the rest is relatively straightforward algebra. Oh yeah, and we like mysteriously add, or multiply another n to this expression, because I'm pretty sure 5 plus 1 equals 6. This is no worry. Just as we were able to just drop unneeded terms when doing this, it's totally valid to say that something like this. It's totally valid to add a term when you're trying to get an expression that's greater than something else. Yeah, so-called immediate from the fact that n is greater than 0. Sure. Now we have a negation proof. For this matter, it kind of shows that there are 10 types of proofs that are going to be encountered in this course. They're all going to be to do with asymptotic notation. So you have the 5 bits of notation. I don't know what the word for that is. The 5 things: big O, big omega, big theta, little o, and little omega. You have each of those 5 and their negations. So if you want to be really, really, really prepared for any quizzes or even assignments that involve this, study all 10. So anyway, if we want to show that a function is not in little o of another function, we'll negate the statement as usual. And we note that this gives us 2 existentially quantified variables. We're going to have to choose a specific m and choose a specific n. As always, we start with the inequality we want and sort of reverse engineer it. Eventually, this sort of stuff becomes routine. Earlier in the course, and particularly the part where I said that assignment 1 is my least favorite, it was kind of Wild West. You would have no ability to predict what a proof with the quantifiers and inequalities will be like. But now that we're focusing on asymptotic notation, every proof will fall into one of those 10 types, and all of them follow a similar procedure. So things should be seeming more familiar, less weird, hopefully. We're going to simplify the complicated side. Subtraction, ooh, a beep beep alarm. We're probably going to use the the factoring out trick. Cool. We have 1 minus some fraction. We want to make that expression into a convenient single value. And the most convenient thing to subtract from 1 is 1/2. So we want 8 over n to be equivalent to 1 over 2. So we're going to place a constraint on n saying that it should probably be greater than 16. And then we replace one of the n's with the value that we chose. Only one of them, partly because we can. More importantly, because the goal is going to be to solve for n. So we have to keep some values or some instances of it around. Now we have a simplified side of the inequality. We combine it with the original, also simple side. And this gives us a simplified inequality. I'm sure I've said this a couple times before, but it's worth repeating. A lot of these things are worth repeating. But we don't really know that this is true yet. The fact that n squared minus 8n is greater than n squared over 2 doesn't imply that n squared over 2 is greater than mn squared. But it's okay to say this in our rough work because it follows the same principle as we used at the beginning of it. We have an inequality that we want to be true, so we're going to start with that inequality and reverse engineer it. This one will be chill. Divide both sides by n squared. And you get that m has to be strictly greater than, or strictly less than 1 over 2. Oh yeah, and that gives us enough to start on the formal proof. Aggravatingly, this slide says that it's equal to 1 over 2, even though we just found that it has to be strictly less than 1 over 2. But this somehow just works because of when m is used in the proof. It's likely that, full disclosure, these slides weren't originally mine. The assignments are made by me, but these slides were made by another instructor. They're sort of the standard slides for this course. So the original author probably did some rough work that found that maybe m has to be less than or equal to 1/2, or maybe that m has to be strictly less than, 3/4. And then they chose m equal to 1/2. The values that you use for these proofs will be different between people, and the constraints you find will probably be different between people. And actually, as I was doing that explanation, I realized that a much simpler thing is probably true. The less strict inequalities the entire time. Not in the original one. You know what, never mind. We're just gonna leave it at the original author probably did something different. For setting n, they used the slightly clunkier version of our max trick. I would have preferred max n naught, n naught 16 plus 1, or even n naught plus 16, but all of these work. All of these will probably get the exact same value. This one and this one will get the exact same value, but this one will be distinct. Either way, it'll work. We set m and n explain some of the properties that we found in our rough work, and then we finish it off just like normal, starting at one side of the inequality and eventually making it to the other. Check out this inequality and all the others and try to justify all the steps with reference to values of m and n. Okay. No chance we have enough time for this one. I might do it in a later class, but I'm okay with leaving it as an exercise for the reader. This kind of throws a curveball at you with the log, so you'll have to figure out how to compare a log of an exponential to a polynomial. Hint, 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 hint. The base of the logarithm and the base of the exponential function are sort of conveniently chosen so that with a bit of fiddling, the log and the exponential will sort of cancel each other out and become a polynomial. It won't be immediately straightforward how they do it because the bases are different, but that's what happens eventually. With the last little bit of the class, I just wanted to look at my draft for the quiz and see if there's anything useful I could tell you about the quiz tomorrow without giving anything away. So give me a moment. Okay, so there will be 4 questions on the quiz. 2 of them are sort of more conceptual. You'll have to know the general idea of asymptotic notation and the hierarchy of functions in order to do similar things to this slide. As I mentioned at the end of last class, there will be a question where you have to match the asymptotic notation definitions to their statements. Again, don't know the word for that. So you'll have to be able to recognize, or you'll have to understand the definitions well enough to recognize them, but you won't have to memorize them. And finally, hope you haven't forgotten about cost functions, because there will be something to do with worst case step counting on the quiz. So yeah, 4 questions. That was an overview of each one. Good luck tomorrow, and yeah, I'll see you then.